right, welcome everybody. Hope you're doing well. Today we're going to talk about equilibrium expressions. So in understanding equilibrium, we have to be able to represent that mathematically. So in order to do that, we write an equilibrium expression. And basically what an equilibrium expression is it's kind of a simple equation. More like a proportion, really. It's also known as the law of mass action. So if you are asked to write a law of mass action, what they're asking you to write is an equilibrium expression. So you're not actually writing a law or anything. They're just asking you to write an equation. And so basically this is the format for your equilibrium expression. So first off, K is going to be equal to the rest of this equation. Now capital K, we're in the big leagues now, so this is big K. This is going to be your equilibrium constant. So this is not kinetics K, this is not lowercase k, this is the equilibrium constant, this is capital K. And so the way that we write this is basically it's going to be the concentration of your product held to the power of its coefficient. Now that's another way that it's different from kinetics. In kinetics, you weren't able to just look at an equation and determine the exponent, aka the order. But in equilibrium constant equations, in laws of mass action, you can. And so it's going to be the product held to its coefficient over the reactant held to its coefficient. So to the power of its coefficient. So let's say that I had this equation, and I know that this looks really dumb, but this is like legit how every book explains it. So let's say you had reactants, capital A and capital B, and they react to form capital C and capital D. Those are your products. And then the lowercase a, b, c, and d would be like their coefficients. Okay, so in the balanced equation, those would be their coefficients. So if I was going to write a law of mass action for this, then my equilibrium expression would look like the following. I would have capital K, so make sure it's capital K, okay, for equilibrium constant, is set equal to products over reactants. So my products are capital C and capital D. Now, capital C is going to be held to the power of its coefficient, which was lowercase c, and capital D is held to the power of its coefficient, which was lowercase d. Okay? And you would be multiplying those two concentrations, each held to the power of their coefficient. Now, the products always go over the reactants. So my reactants are capital A and capital B, each held to the power of its coefficient. And again, you'd be multiplying those two. So it would be the product of your products divided by the product of your reactants, each held to the power of their coefficient. Okay, so let's talk about K for a second then, this capital K thing. So here's the deal. Let's say you have a K greater than 1. Well, think about it. If this thing is a fraction, right, and you have K greater than 1, that means that whatever value is on the top of this proportion is greater. And in this case, that means we have more products. So if you have an equilibrium constant greater than 1, that means that when this reaction reaches equilibrium, when the concentration of reactant and product starts to become constant, right? So at equilibrium, you end up with more products than reactants, right? Because the top of this proportion is greater. And so we say that the reaction favors the products. Okay, so when this reaction happens, you're going to end up with more products than reactants. So if K is less than 1, then that's, exactly the opposite, right? If this proportion is less than 1, that's because the bottom of the proportion is greater than the top. And so when the bottom is reactants, that means that the system is going to have more reactants at equilibrium, aka the reaction favors reactants. So you're not going to get as many products. Okay, so rules for this, right? I mean, it looks simple enough, right? But there's always going to be some rules. So first off, always products over reactants. Put a little exclamation on it. It's always products over reactants. Okay, so don't get that confused. Another thing, we always leave out pure solids. So anything in the equation that's followed by an S in parentheses, and also liquids. Pure liquids. So if it's got an L after it in the chemical equation, they're not included in these equilibrium expressions. Why not? Well, they don't have a concentration. There's literally nothing I can put in those brackets. I can't mathematically measure the concentration of a solid or a pure liquid, so we just don't include it. We leave it out of the equilibrium expression. Okay? So another important point here, okay? You know, chemistry, we always got to have more than one way to explain things, right? And so your capital K, your equilibrium constant, can also be written as K sub C, right? So your equilibrium constant using concentration. That's why we use the C right there. And sometimes it's even called KEQ, just equilibrium constant. I guess because there's so many dang K's in chemistry, right? So anyway, all three of those K's mean exactly the same thing. And if you're writing an equilibrium expression for K or KC or KEQ, then it's written using the concentrations of the reactants and products. Which most of the time is going to be molarity, right? So whatever molarities are given to you, then you put those in the brackets and hold everything to the power of its coefficient, okay? However, KC, KEQ, or just plain old K, is not the same thing as KP. Isn't that great, right? Not confusing at all. So if we're using concentrations, it's just plain old K or KC or KEQ. However, KP is a different ballgame. KP is written using the partial pressures of gases. Okay, so we said that we take out pure solids and we take out pure liquids because they don't have a concentration or anything that I can plug into the brackets. But pressures are numbers that we can plug into the brackets. And so we can use partial pressures to get KP, okay? And it's written exactly the same way. You do products over the reactants with everything held to the power of its coefficient in the balanced chemical equation. Now, here's the deal. Like we said, your K or KC or KEQ is written using, you know, concentration, aka molarity, right, in the brackets. The other one is written using pressures, and so those are usually going to be in parentheses instead of brackets. So there you go. So if you see something with parentheses instead of brackets, you're probably dealing with KP. If you see brackets, you're probably dealing with KC. Okay? Now, we can convert one K value to the other. So I can take a KC written using concentration, and I can mathematically convert that to KP, or vice versa. And so the equation for that is KP is equal to your KC, so the one written using concentration, multiplied times R times T to the power of delta N. All right, so alphabet soup, right? So R is your gas constant. Right, and if you're, as long as you're using atmospheres, it's going to be that 0.0821 liters times atmospheres over moles times Kelvin. So that same one from the ideal gas law, okay? It's that same R value. And temperature, that's T. And that's got to be in Kelvin. Another K. Okay, but your temperature has to be converted to Kelvin if it isn't already. And then delta N. So delta always means change, right? So it's a difference. It's a difference in a number of moles of gas. So basically the way that you calculate delta N is you take the number of moles of gaseous product and you subtract the number of moles of gaseous reactant. I'm just going to abbreviate that because I'm out of space. And so the difference between the moles of gas of product and the moles of gas of reactant, so the difference in moles from the beginning to end of the equation, that's going to be your change in moles of gas. So you would put that number there as an exponent, okay? Now another thing is sometimes you are going to be using Hess's law. And so you'll have a bunch of different equations that you use to build one equation. Or let's say that you are dealing with a reaction mechanism and you have several elementary steps that you have equilibrium constants for, but you need to know the equilibrium constant for the entire reaction. Okay, so if we have to manipulate equations, So if we have to double them or triple them or reverse them, flip them around backwards or whatever, we have to adjust k accordingly. And so here's the deal. Let's say that I have to double an equation, right? Or triple an equation to make this work. Anytime you multiply an equation, k is going to be held to that power. So it would be k to the power of whatever you multiplied the equation by. So let's say that you doubled the equation. Well, then you would take your k value and put it to the power, you'd square it, be to the power of 2, right? And so that value would be your new k value. Or let's say that you tripled your equation, right? Then you would take your existing k, put it to the power of 3, aka cube it, and that would be your new k value. So if you multiply the entire equation, all of the coefficients in an equation by some number, you're going to put k to the power of that same number, okay? When an equation is reversed, so let's say I have to flip it around and make my products reactants and my reactants products, then what we're going to do is take the reciprocal of k. So it'd be 1 divided by k. Why? Well, let's go back to what we were talking about, right? So remember that it's always products over reactants, correct? Well, if I flip it around, I'm literally flipping that proportion around. And so basically you just take the reciprocal, right? Okay, and then the last thing, when you add equations together, so when adding equations together to get a final overall equation, you need to multiply the k values for each of the equations you're adding together. So you'll take, your first k for the first equation, multiply it by the second k for the second equation, multiply it by the third k for the third equation, and on it goes until you run out of k's. Okay? So if you have to manipulate equations, this is how you manipulate k accordingly. Okay, have fun with this.